Hello friends, once again a very warm welcome to all of you to Entrance Chemistry YouTube channel. Today we will discuss Maxwell-Boltzman Statistics. As you know, statistical thermodynamics relates thermo and quantum mechanics. Here we have to deal with large number of particles, so we use statistics. Particles are here two types, distinguishable or classical particles and indistinguishable or quantum mechanical particles. These distinguishable or classical particles are studied under Maxwell-Boltzman Statistics, and the other one, that is indistinguishable or quantum mechanical particles, are studied under Bose-Einstein and Thermodynamic statistics. Now let's discuss Maxwell-Boltzman statistics briefly. Consider a system of large number of particles, that is n number of particles, which composed at a temperature T, and the system contains constant energy E. So here number of particles is constant, energy is also constant, and temperature is also constant. Then see what are the characteristics that the particles should have to be studied under Maxwell-Boltzman statistics. The first characteristic is particles don't interact each other. That means particles don't attract or repel each other. The second condition or second characteristic is particles are distinguishable from each other. We have already stated in the beginning that Maxwell-Boltzman statistics is only applicable to distinguishable particles, not to indistinguishable particles. Indistinguishable particles are studied under Bose-Einstein and Thermodynamic statistics. So, in Maxwell-Boltzman statistics, the characteristics of particles should be distinguishable. Next characteristic is each energy state contain any number of particles. That is, there is no restriction. A restriction such as each energy state will carry one particle. These restrictions are not seen or are not the characteristics of Maxwell-Boltzman statistics. So, each particle may exist in a number of energy levels also. So, any number of particles present in any energy level, and any particle may exist in a number of energy levels. But the total energy is a constant, that is E, and the total number of particles is constant N. Consider the distribution of a total energy among various energy levels E1, E2, E3 up to EI number of energy levels are present. Similarly, in E1 energy level, there are N1 number of particles. In E2 energy level, there are N2 number of particles. In E3 energy level, there are N3 number of particles. And in EI energy level, there are Ni number of particles. We can also write like this. N0 number of particles possess E0 energy. N1 number of particles possess E1 energy up to EI energy level, which contains Ni number of particles. So Ni number of particles possess Ei energy. And this is the ground state energy level. Okay, now see what will be the value of E. Here E0 energy is possessed by N0 number of particles. So here the energy value will be N0 E0. Similarly, in E1 energy level, total number of particles are N1. So here the energy will be N1 E1, and here the energy will be Ni Ei. So the total energy will be the summation of Ni Ei, or we can write N0 E0 plus N1 E1 plus N2 E2 up to Ni Ei. So the total energy is summation of Ni Ei, and the total number of particles is summation of Ni. Now let's find out thermodynamic probability, which is the number of ways in which n particles can be put in these energy levels. The mathematical expression for W is W equal to n factorial upon n0 factorial into n1 factorial into n2 factorial up to ni factorial. Taking logarithm on both sides, what will happen? Ln W equal to ln n factorial upon n0 factorial, n1 factorial, n2 factorial upon ni factorial, and we will mark this as equation 1 and this as equation 2. Now if we will solve this, what will happen? Ln W equal to ln n factorial minus ln n0 factorial n1 factorial, n2 factorial up to ni factorial. We can write this ln n0 factorial plus ln n1 factorial plus ln n2 factorial up to ln ni factorial. If we replace this as ln n factorial minus summation of ln ni factorial, so our ln W becomes ln n factorial minus summation of ln ni factorial. See, this is a very large quantity. We cannot determine it accurately. To determine it approximately, we use stirring formula. Or by stirring approximation formula, what will happen? According to Stiring approximation formula, ln x factorial equal to x ln x minus x. So, if we put this formula here and here, what will happen? Ln n factorial will be n ln n minus n, and ln ni factorial will be ni ln ni minus ni. If we will put the summation sign or sigma, we will get summation of ln ni factorial equal to summation of ni ln ni minus summation of ni, or summation of ln ni factorial equal to summation of ni ln ni, and summation of ni is what? Capital N. So, we will put this value, that is value of ln n factorial and ln summation ln ni factorial here. We mark it equation 3. So, putting these values in equation 3, what we will get? Ln w equal to, when we will solve it, we'll get n ln n minus summation of ni ln ni plus n, and this will be cancelled out. What will remain? N ln n minus summation of ni ln ni. This is ln w. We marked it equation 6. Now, if we consider the most probable distribution of particles in the system, then W value is maximum. So, what will happen? As the W value is maximum, derivative of W is equal to 0. Also, derivative of ln W is equal to 0 because W is here constant. As W is a constant, ln W will be also a constant. We will put this value. Let's determine del ln W. Here, this will be 0 because n is a constant. That means n ln n is also a constant. So, what will happen? 0 equal to 0 minus del summation of ni ln ni. Now, putting this formula, we will determine the derivative of this one. So, what will happen? That implies summation of ni ln ni equal to 0. It will determine this derivative, what will happen? Ni into del of, we have just missed here del sign, so del ln ni plus ln ni into del ni equal to 0. That implies summation ni, derivative of ln ni is 1 by ni into del ni plus ln ni del ni equal to 0. That implies summation del ni plus summation ln ni del ni equal to 0. Let's mark it equation 5. We know del n equal to summation of del ni. It's a constant, so what will be the value? 0. Similarly, del E equal to summation of EI into del Ni. Its value is also 0. Let's mark it equation 6 and mark it as equation 7. So now we will put Lagrange undetermined multipliers. Lagrange undetermined multipliers. That is, multiplying equation 6 with an constant, that is alpha, and multiplying equation 7 with another constant, that is beta, and then add to equation 5. Here del ni will be 0, so equation 5 will take the form as summation ln ni del ni equal to 0. Let's mark it as equation 5 dash. So equation 6 into alpha plus equation 7 into beta plus equation 5 dash. We will multiply two different constants with these equations and then add to equation 5 dash. This is our Lagrange undetermined multipliers. We will multiply different constants and then add to these equations. That is alpha into del ni, beta into summation ei del ni plus equation 5 dash, that is summation ln ni del ni equal to 0. We can also write this equation as summation alpha plus beta ei plus ln ni del ni equal to 0. From Maxwell-Boltzmann particles characteristics, that is, particles don't attract or repel each other, are independent of each other, so this value cannot be 0. If two values are multiplied and the value becomes 0 and its value is not 0, then whose value is 0? This value will be 0. So we will write alpha plus beta EI plus ln Ni equal to 0. If we'll keep ln Ni on left side and we'll took this 2 to right side, what will happen? Minus alpha minus beta EI. Now changing ln to E, we will get Ni equal to e to the power minus alpha minus beta EI. Or we can write this as Ni equal to e to the power minus alpha into e to the power minus beta EI. We know beta is equal to 1 by kt. Beta is equal to 1 by kt. So what will be the value of Ni now? Ni equal to e to the power minus alpha into e to the power minus 1 by kt EI. This one marked as 8 number equation, and this is 9, and this is equation 10. So this expression is for Maxwell-Boltzmann distribution statistics for non-degenerate energy levels. It is for non-degenerate energy levels. If we will write for degenerate energy levels, because it is possible that there may be a number of quantum levels of degenerate energies. So what will happen then? Ni will be equal to Gi into e to the power minus alpha into e to the power minus epsilon I, Ei e to the power minus Ei by kt. So this is the Maxwell-Boltzmann distribution law for degenerate energy levels, and here why Gi is multiplied? Because Gi is the statistical weight factor for degenerate energy levels. Now if we will write the general form of Boltzmann distribution law, that is Ni upon capital N. So Ni is written as such, and capital N is a summation of Ni. So we can write Ni is here, that is Gi into e to the power minus alpha into e to the power minus Ei by kt, and what will be capital N, that is summation of Ni, summation of Gi into e to the power minus alpha into e to the power minus Ei upon kt. And this is what the general form of Maxwell-Boltzmann statistics. This is an important question for PG semester exams. I hope it will be helpful for you. Thank you.